Great scientific journeys rarely begin with applause. They begin quietly, with curiosity. In the case of Sabrina Pasterski, the seeds of her later recognition as a rising star in theoretical physics were planted long before headlines ever mentioned her name. To understand why some call her the next Einstein, we must first understand the environment, mindset, and early influences that shaped her. Sabrina Gonzalez Pasterski was born in Chicago, Illinois, in 1993. From an early age, she displayed a level of curiosity that went beyond ordinary childhood wonder. Many children ask why. Sabrina asked how, and what if. This difference may seem subtle, but in science it is profound. Why seeks explanation, how seeks mechanism, what if seeks possibility. These are the questions that fuel theoretical physics. Her upbringing played a significant role in nurturing this mindset. Her parents encouraged exploration rather than passive consumption. Instead of being told to simply memorize facts, she was encouraged to investigate them. This distinction is critical. Memorization builds students. Investigation builds scientists. Chicago itself has a strong intellectual culture, with major universities, research institutions, and a history of scientific innovation. While she was not yet part of that academic world, the cultural atmosphere around her valued education and intellectual pursuit. But environment alone does not produce genius. What sets certain individuals apart is how they respond to opportunity. In Sabrina's case, her response was action. As a child, she showed a deep interest in mathematics and physics. These subjects are often intimidating to students because they demand abstract thinking. Many people prefer subjects with immediate, tangible results. Mathematics and theoretical physics require comfort with symbols, patterns, and invisible structures. Sabrina was not intimidated by abstraction. She was drawn to it. Teachers quickly recognized her abilities. But what made her different was not simply that she excelled in class. It was that she seemed internally motivated. She did not pursue learning for praise or recognition. She pursued it because she genuinely wanted to understand the world at its deepest level. This internal motivation is a defining characteristic of many great physicists. Albert Einstein himself once described curiosity as more important than intelligence. Intelligence can solve problems that are presented. Curiosity discovers problems no one has yet noticed. In Sabrina's early years, curiosity was already her driving force. Her fascination with flight is a powerful example. Airplanes are marvels of applied physics. They demonstrate lift, drag, thrust, aerodynamics, and the delicate balance between stability and control. To most observers, a plane taking off is simply impressive. To a young mind like Sabrina's, it was a question waiting to be explored. How can something so heavy rise into the sky? This question would not remain theoretical for long. While many teenagers are exploring hobbies or social interests, Sabrina began studying aviation seriously. She did not merely want to understand flight in theory. She wanted to experience it, build it, test it. This distinction between passive knowledge and active mastery defines her early development. Her early education was not just about high grades. It was about building intellectual confidence. Confidence in science is not arrogance. It is the willingness to attempt difficult problems without fear of failure. Theoretical physics demands this mindset. Equations fail, hypotheses collapse, mathematical paths lead to dead ends. Only those comfortable with intellectual risk can persist. Sabrina's formative years cultivated exactly that resilience. It is important to recognize how unusual this combination is. Many students are strong in mathematics but hesitant in application. Others are hands-on builders but less drawn to abstract theory. Sabrina showed early signs of blending both tendencies. She could appreciate equations and also envision their real-world implications. This dual capability would later define her career in theoretical physics, where abstract mathematics must describe physical reality. But even in her youth, the pattern was visible. She was not satisfied with surface-level understanding. Another essential element in her early life was discipline. Curiosity alone is not enough to produce mastery. Scientific achievement requires sustained effort. Mastering advanced mathematics at a young age demands focus beyond what is typical for teenagers. The patience required to work through complex problems is immense. Sabrina's discipline became especially evident when she turned toward aviation engineering as a teenager. Studying aerodynamics, structural design, and mechanical systems requires precision. Small mistakes can have enormous consequences. This level of responsibility forces maturity. Her early years were therefore not just about brilliance. They were about responsibility, responsibility to detail, responsibility to safety, responsibility to accuracy. These traits are foundational in physics, where even a small error in reasoning can invalidate an entire theory. In addition, her upbringing appears to have emphasized independence. Independence in thought is perhaps the most critical trait for a theoretical physicist. Progress in fundamental physics does not come from repeating accepted ideas. It comes from questioning them. As a young student, Sabrina did not appear driven by comparison with peers. She was not chasing status. She was chasing understanding. This distinction becomes clearer when we examine her later academic life, where she reportedly avoided obsessing over grades and focused instead on research and ideas. That mindset does not appear suddenly in adulthood. It is cultivated early. Her intellectual development also benefited from exposure to real-world challenges. Abstract learning in a classroom is important, but applying that knowledge solidifies understanding. When a young student sees physics not as textbook material, but as the governing language of reality, the subject transforms from academic requirement to personal mission. By her teenage years, Sabrina had already begun stepping into that mission. It is also worth noting the role of problem solving. Some students excel in structured environments where problems have clear solutions. Theoretical physics, however, is filled with problems whose solutions are unknown even to experts. Early comfort with open-ended challenges builds the mental flexibility required for frontier research. In her formative years, Sabrina demonstrated comfort with precisely this kind of challenge. She did not shy away from complexity. She leaned toward it. Another defining feature of her early development was humility. Despite remarkable achievements, she maintained a low public profile. She did not cultivate fame. She did not aggressively self-promote. Instead, she allowed her work to speak for itself. This quiet confidence is reminiscent of many scientists whose focus remains on discovery rather than recognition. Humility, in scientific terms, is essential. Nature does not yield her secrets to ego. The universe is indifferent to personal ambition. Only careful observation, rigorous reasoning, and intellectual honesty uncover truth. Sabrina's early years appear to have instilled respect for that process. As her education advanced, it became clear that she was not simply talented. She was purpose-driven. There is a difference. Talent can fade without direction. Purpose sharpens talent into impact. Her early decisions suggest that she already sensed her calling within physics. The development of a future theoretical physicist begins not with complex equations, but with mindset, comfort with abstraction, hunger for understanding, willingness to challenge assumptions, discipline to pursue difficult paths, independence in thought, humility before evidence. All of these qualities were forming in Sabrina Pasterski long before she entered elite universities. When observers later began calling her the next Einstein, they were responding not just to academic credentials, but to this foundation. Einstein himself was shaped by early curiosity, independent thinking, and resistance to passive acceptance of authority. The comparison is not about claiming identical genius. It is about recognizing similar intellectual temperament. It is also important to emphasize that labeling someone the next Einstein can be misleading. Scientific progress is not about replacing legends. It is about extending understanding. Sabrina's early life did not prepare her to imitate Einstein. It prepared her to ask her own questions. The most powerful legacy of her formative years is this: she learned to trust her curiosity. In a world that often rewards conformity, she followed inquiry. In an educational system that can sometimes prioritize testing over thinking, she prioritized depth. As she moved toward higher education, these traits would amplify, but the roots were already planted. The disciplined teenager studying aerodynamics, the curious child asking mechanism-based questions, the independent thinker uninterested in superficial achievement, the humble student focused on understanding rather than applause. Great physicists are not created in a single breakthrough moment. They are shaped gradually through habits of mind developed early and reinforced consistently. By the time Sabrina Pasterski stepped into the world of advanced theoretical research, she was not beginning her journey. She was continuing one that had started in childhood. Her early life demonstrates a powerful lesson. Brilliance is not merely about intelligence. It is about mindset. It is about how one responds to curiosity. It is about whether questions are ignored or pursued relentlessly. In Sabrina Pasterski's case, they were pursued. And that pursuit would carry her from a curious child in Chicago to the forefront of modern theoretical physics, where the deepest questions about black holes, spacetime, and quantum gravity await answers. Before the world ever compared her to Einstein, the essential qualities were already present: quiet, disciplined, and determined, forming the foundation of a physicist prepared to explore the very structure of reality itself. There are moments in a young person's life that reveal whether their curiosity is casual or committed. For Sabrina Pasterski, that defining moment came not in a classroom, not during an exam, but in a garage, surrounded by aluminum sheets, rivets, tools, engineering manuals, and an idea that most adults would never dare to attempt. At just 14 years old, she decided she would build an airplane. To understand the magnitude of that decision, we must pause. Building a real aircraft is not a science fair project. It is not assembling a model kit. It is a complex engineering endeavor governed by strict aerodynamic principles, structural requirements, weight distributions, mechanical systems, and safety regulations. Even trained engineers approach such work with caution. Yet a teenager, driven by curiosity and discipline, stepped into that challenge with confidence. Her choice was not impulsive. It grew from her deep fascination with flight. Airplanes represent applied physics at its finest. Every takeoff is a demonstration of Bernoulli's principle, Newton's laws of motion, pressure gradients, thrust to weight ratios, and structural engineering precision. For most students, these ideas remain abstract symbols on a page. For Sabrina, They became physical realities she could touch and test. She began constructing a single-engine airplane from a kit, but this does not diminish the achievement. Aircraft kits require builders to assemble and integrate complex systems with exacting standards. Each rivet must be placed correctly. Each structural component must align within tight tolerances. Wiring, fuel systems, control surfaces, and engine integration must function flawlessly. A minor miscalculation could compromise safety. The process demanded extraordinary patience. Unlike many teenage hobbies that deliver quick gratification, building an airplane requires months, sometimes years of careful, repetitive, meticulous work. Precision becomes a daily discipline. The builder must measure, adjust, remeasure, and verify continuously. This cultivates a mindset essential for both engineering and theoretical physics: respect for detail. What makes this episode even more remarkable is not just that she completed the aircraft, but that she flew it. After construction, the plane underwent inspection and certification by the Federal Aviation Administration. Passing FAA standards is no symbolic gesture. It requires compliance with rigorous safety and engineering regulations. Her aircraft met those standards. Imagine the psychological landscape of that first flight, sitting in a machine you built with your own hands, knowing that every component, every connection, every control cable was assembled by you. There is no separation between theory and reality in that moment. Physics is no longer an equation, it is survival. Lift must exceed weight. Thrust must overcome drag. Structural integrity must hold under stress. When the plane lifted off the runway, it was more than an aviation milestone. It was proof of intellectual courage. It demonstrated that she did not merely study physics, she embodied it. This experience shaped her in several profound ways. First, it eliminated fear of complexity. Many students avoid advanced scientific challenges because they appear overwhelming. Building an aircraft requires breaking down enormous complexity into manageable tasks, one rivet at a time, one panel at a time, one system at a time. This incremental mastery mirrors the way theoretical physicists tackle monumental questions, by decomposing them into solvable components. Second, it reinforced the unity between theory and application. In physics, equations describe reality, but until one sees those equations manifested physically, they can feel distant. Through aviation, Sabrina saw how mathematical models govern tangible outcomes. If your calculations are wrong, the plane does not fly correctly. There is no room for intellectual laziness. Third, it cultivated accountability. When a student solves a math problem incorrectly, the consequence is a lower grade. When an engineer miscalculates structural load, the consequence can be catastrophic. Working on an aircraft instills a seriousness that textbooks alone cannot provide. It builds respect for accuracy, a trait indispensable in advanced research. This phase of her life also revealed independence. Teenagers are often influenced heavily by peer culture, yet building an airplane is not a socially common hobby. It requires stepping outside conventional teenage life. It demands time, solitude, focus, and long-term commitment. That willingness to follow a path different from one's peers is a defining trait of innovators. Albert Einstein once worked quietly in a patent office while developing revolutionary ideas about space and time. Intellectual independence often looks unusual at first. In Sabrina's case, spending teenage years immersed in aircraft construction signaled that she was guided by inner motivation rather than external approval. Another important dimension of this achievement was resourcefulness. Engineering projects inevitably encounter obstacles. Parts may not fit perfectly, adjustments may be necessary, unexpected problems arise. Overcoming these requires creativity within constraints, a balance between imagination and discipline. This balance is precisely what theoretical physics demands. One must imagine possibilities beyond current understanding, yet remain constrained by mathematical consistency and empirical evidence. The mindset developed in building a plane, creative but exact, parallels the mindset required to explore black holes and quantum gravity later in her career. The project also attracted attention beyond her immediate circle. When she later applied to the Massachusetts Institute of Technology, she submitted a video of her completed aircraft as part of her application. The video was not a boastful display. It was evidence of capability. It showed admissions officers something grades alone could not: initiative, depth, and execution. MIT recognized what that airplane represented. It was not merely mechanical skill. It was proof of intellectual maturity. She was accepted, beginning the next phase of her scientific journey. But the airplane remains symbolic. It symbolizes courage, the willingness to attempt something extraordinary at a young age. It symbolizes integration, merging physics, engineering, mathematics, and discipline into one project. It symbolizes vision, seeing beyond what is typical for someone her age. Most importantly, it symbolizes refusal to accept limits imposed by expectation. Society often categorizes teenagers into narrow possibilities: student, athlete, hobbyist. Building and flying an aircraft challenges those assumptions. It sends a powerful message: capability is not strictly tied to age. When curiosity is paired with discipline, remarkable achievements become possible. There is also a deeper philosophical dimension to this story. Flight has long been associated with human aspiration. For centuries, humanity dreamed of rising into the sky. The Wright brothers transformed that dream into reality through experimentation and persistence. In building her own airplane, Sabrina connected to that lineage of innovators who refused to accept gravity literally and metaphorically. Gravity pulls downward, limits constrain possibility. To build and fly is to defy both. This mindset, challenging fundamental forces, later echoes in her academic work. As a theoretical physicist, she studies gravity at its most extreme in black holes. The same force that keeps airplanes grounded is the force she now analyzes at cosmic scales. The teenager who mastered aerodynamics would become the researcher probing spacetime itself. Her airplane experience also reinforced an important scientific principle: reality is unforgiving. Equations must correspond to nature. There is no room for superficial understanding. Either the plane flies safely, or it does not. Either the structure withstands stress, or it fails. This binary clarity sharpens analytical thinking. Moreover, the process likely strengthened her tolerance for delayed gratification. In an era of instant results, building an aircraft requires sustained effort over long periods. Each day's work may appear minor, but cumulative progress yields transformation. The same patience is essential when working on unsolved problems in theoretical physics that may take years to clarify. It is tempting to romanticize this story, but its real power lies in discipline, not drama. The hours spent drilling, aligning, calibrating, and testing were not glamorous. They were methodical, and greatness often hides inside method. When observers later labeled her the next Einstein, they saw her academic achievements at Harvard and Princeton. But the roots of that recognition stretch back to a garage workshop. Before she explored the curvature of spacetime, she ensured the curvature of her aircraft wings was precise. Before she studied quantum gravity, she mastered the gravity affecting her own flight. In that sense, building and flying her airplane was not separate from her physics career. It was preparation. It demonstrated that she could take an enormous challenge, break it into parts, maintain focus through complexity, and bring theory into reality. Those qualities define not just engineers, but pioneers. At 14, Sabrina Pasterski did more than build a machine. She built confidence. She built resilience. She built proof that her curiosity could produce tangible achievement. And when that airplane rose into the sky, it carried more than a pilot. It carried the early confirmation that her mind was capable of extraordinary things. Long before Harvard, before black hole research, before global recognition, there was a runway, an engine's roar, and a teenager who trusted physics enough to leave the ground in a machine she built. Herself, that moment did not make her a physicist. It revealed that she already was one. When Sabrina Pasterski entered the Massachusetts Institute of Technology, she was no longer just a talented teenager who had built and flown her own airplane. She was stepping into one of the most demanding intellectual environments in the world, a place where brilliance is common and expectations are relentless. MIT is not impressed easily. It is an institution built on rigor, competition, and innovation. To thrive there requires more than talent. It requires resilience, independence, and depth. From the beginning, Sabrina distinguished herself not through loud ambition, but through quiet intensity. She chose to major in physics, one of the most mathematically demanding and conceptually challenging disciplines available. Physics at MIT is not simply about solving textbook problems. It demands the ability to think abstractly, to visualize invisible structures, to manipulate advanced mathematics, and to persist through confusion. It is designed to stretch even the strongest minds. What set her apart was not just her capacity to understand complex material, but her approach to learning. Many high-achieving students measure their success by grades, rankings, or recognition. Sabrina reportedly did not even check her grades online. This detail, often repeated in discussions about her, is revealing. It suggests a mindset focused not on performance metrics, but on mastery. She was interested in understanding, not applause. This attitude is rare in competitive academic environments. When external validation disappears as a motivation, only genuine curiosity remains, and genuine curiosity is the fuel of original research. During her undergraduate years, she did not wait passively for instruction. She sought research opportunities early. Research in physics is different from coursework. In class, problems have known answers. In research, the answers are unknown even to professors. Engaging in research as an undergraduate requires intellectual courage. It means stepping into uncertainty. At MIT, she worked under Professor Alan Haggerty and completed a senior thesis that explored theoretical aspects of gravitational lensing and related topics. Gravitational lensing, the bending of light around massive objects, is a direct consequence of Einstein's theory of general relativity. Studying it requires deep engagement with differential geometry, space-time curvature, and mathematical modeling. Her thesis earned high praise, but more important than praise was the direction it signaled. She was not gravitating toward applied physics or engineering alone. She was moving toward the foundations of physical law, the deep structure of reality described by mathematics. After graduating from MIT with honors, she continued her academic journey at Harvard University, entering one of the most prestigious PhD programs in theoretical physics. Harvard's physics department has produced Nobel laureates, groundbreaking discoveries, and leaders in quantum field theory, cosmology, and particle physics. Admission alone reflects exceptional capability. Thriving there requires sustained excellence. At Harvard, Sabrina immersed herself in one of the most challenging areas of modern science, the intersection of quantum mechanics and general relativity. This frontier is often described as the search for quantum gravity, a unified framework that reconciles the laws governing the very large with those governing the very small. To appreciate the difficulty of this pursuit, consider the landscape of modern physics. General relativity describes gravity as the curvature of spacetime caused by mass and energy. It works beautifully for planets, stars, and galaxies. Quantum mechanics, on the other hand, describes particles and forces at microscopic scales with extraordinary precision. Yet when scientists attempt to combine these theories in extreme conditions, such as inside black holes or at the beginning of the universe, contradictions emerge. Resolving these contradictions is one of the greatest intellectual challenges of our time. It requires mathematical sophistication at the highest level, along with conceptual clarity about what physical laws truly mean. Sabrina's research at Harvard focused on aspects of black hole physics, gravitational scattering amplitudes, and the subtle symmetries of spacetime known as asymptotic symmetries. These topics are not widely understood outside specialist circles, but they sit at the cutting edge of theoretical inquiry. One area connected to her work involves what are called soft theorems in quantum field theory. These theorems describe how low-energy particles behave during scattering processes. Surprisingly, recent research has revealed deep connections between these soft theorems and the symmetries of spacetime at infinity, regions far removed from local interactions. These insights may hold clues about how information is preserved in gravitational systems, including black holes. This line of research connects directly to the famous black hole information paradox, a puzzle that troubled Stephen Hawking for decades. If black holes evaporate through Hawking radiation, what happens to the information about the matter that fell into them? Quantum mechanics insists that information cannot be destroyed, yet classical interpretations of black holes suggest otherwise. This tension strikes at the heart of physical law. By exploring mathematical structures underlying spacetime symmetries, Sabrina contributed to efforts aimed at clarifying these paradoxes. Such work requires extraordinary abstraction. The equations involved are dense, subtle, and unforgiving. Progress often occurs in small conceptual steps rather than dramatic breakthroughs. Her growing reputation within theoretical physics circles did not arise from media attention. It emerged from serious academic contribution. She published in respected journals, collaborated with leading physicists, and presented research at conferences attended by global experts. It is during this phase that comparisons to Einstein began circulating in popular media. The comparison was not based on a single revolutionary discovery. Instead, it reflected the perception that she was working at the foundational level of physics, asking questions about gravity, spacetime, and the fundamental structure of reality, much as Einstein once did. However, there is an important distinction to maintain. Einstein developed general relativity largely through independent reasoning during an era when theoretical physics was less specialized. Modern theoretical physics is vastly more complex. Today's researchers build on a century of accumulated mathematical development. Collaboration, peer review, and technical specialization define the field. Sabrina's rise within this environment demonstrates adaptability. She entered a landscape filled with towering intellectual frameworks, quantum field theory, string theory, holography, and advanced geometry, and navigated it successfully. This requires not only intelligence, but humility and persistence. One must accept that understanding comes gradually. Another defining feature of her academic ascent is her low public profile. She reportedly does not maintain active social media accounts and avoids unnecessary publicity. In an age where visibility often overshadows substance, this restraint reinforces her focus on research. Her academic journey also highlights the importance of mentorship and intellectual community. At Harvard, she worked alongside prominent physicists who themselves contribute to frontier research. Exposure to such an environment sharpens thinking. It forces clarity. It demands precision. Yet thriving in such a community also requires confidence. Theoretical physics seminars can be intense. Ideas are challenged rigorously. Assumptions are dissected. Only those comfortable defending their reasoning can grow within that space. Sabrina demonstrated the capacity to engage at that level. As her doctoral work progressed, her name appeared increasingly in discussions about young physicists to watch. Fellowships and recognition followed. But again, the attention was secondary. What mattered was that she was participating in humanity's deepest intellectual quest, understanding the fundamental rules governing the universe. This stage of her life represents transformation. The teenager who built an airplane had already demonstrated technical skill and discipline. The undergraduate at MIT proved she could master advanced physics. At Harvard, she entered the realm where new knowledge is created. Creation of knowledge is different from consumption. It involves confronting uncertainty directly. It requires tolerating long periods without clear answers. Many promising students struggle at this stage because the transition from structured learning to open-ended research is psychologically demanding. Sabrina appears to have embraced that uncertainty. In doing so, she became part of a generation of physicists seeking clarity in a landscape shaped by Einstein, Hawking, and others. But rather than attempting to replicate their paths, she works within contemporary frameworks, contributing to collective progress. Her rise from MIT to Harvard symbolizes more than academic advancement. It reflects intellectual maturation. She moved from mastering established principles to exploring their limits, from solving known equations to questioning their completeness, from student to contributor. That journey, from disciplined undergraduate to theoretical researcher, is why her name carries weight within scientific circles. It is not hype alone. It is the steady accumulation of rigorous work at the highest level of abstraction. The phrase "next Einstein" may capture headlines, but the deeper reality is this: Sabrina Pasterski represents the continuity of foundational inquiry in physics. She stands within a tradition of thinkers who refuse to accept that current theories are final. Her academic ascent illustrates that genius is not a single flash of insight. It is sustained engagement with the hardest problems available. It is patience with complexity. It is loyalty to curiosity over recognition. From MIT rigorous classrooms to Harvard's advanced research halls, she demonstrated that her early promise was not accidental. It was preparation for immersion in the deepest questions physics can ask. And in that immersion, she joined the ongoing effort to understand gravity, space-time, and the quantum structure of reality, the same profound mysteries that once captivated Einstein himself. At the frontier of modern physics lies a profound tension, a fracture between two of the most successful theories ever created. On one side stands general relativity, Albert Einstein's masterwork describing gravity as the curvature of spacetime. On the other side stands quantum mechanics, the mathematical framework governing particles and forces at the smallest scales. Each theory works astonishingly well within its domain, yet when brought together under extreme conditions, such as inside black holes or at the birth of the universe, they clash. It is precisely within this intellectual fault line that Sabrina Pasterski's research operates. To appreciate the depth of her work, we must first understand the problem. General relativity tells us that massive objects bend spacetime. Planets orbit stars because they move along curved paths in this warped geometry. Black holes form when matter becomes so dense that spacetime curvature becomes extreme, creating a region from which not even light can escape. Quantum mechanics, by contrast, describes reality in terms of probabilities, wave functions, and discrete energy exchanges. It insists that information about physical systems is never truly destroyed. The evolution of quantum systems is reversible at the fundamental level. Here lies the paradox. In the 1970s, Stephen Hawking discovered that black holes are not entirely black. Due to quantum effects near the event horizon, they emit radiation, now called Hawking radiation. Over immense timescales, black holes can evaporate. But if a black hole completely evaporates, what happens to the information about the matter that fell into it? According to classical reasoning, that information disappears forever. According to quantum mechanics, that cannot happen. This contradiction is known as the black hole information paradox. It is not a minor inconsistency. It challenges the very foundations of physical law. Sabrina Pasterski's work engages with this paradox through a subtle and highly mathematical pathway, the study of spacetime symmetries and scattering amplitudes. Symmetry in physics is not merely aesthetic balance. It is a guiding principle that determines what laws are possible. Emmy Noether proved that every continuous symmetry in nature corresponds to a conservation law. For example, symmetry in time leads to conservation of energy. Symmetry in space leads to conservation of momentum. In recent years, physicists have uncovered deep connections between certain hidden symmetries of spacetime and low-energy particle behavior. These symmetries, known as asymptotic symmetries, describe how spacetime behaves at its boundaries, at infinity, far from localized interactions. At first glance, infinity might seem irrelevant, but in gravitational physics, what happens at the boundaries of spacetime can encode crucial information about what occurs inside it. The mathematics becomes intricate, involving advanced geometry and quantum field theory. Pasterski has worked on understanding how soft particles, extremely low energy quanta, relate to these asymptotic symmetries. In quantum field theory, scattering amplitudes describe how particles interact and transform when they collide. Surprisingly, certain universal patterns appear when very low energy particles are involved. These patterns are governed by soft theorems. Researchers discovered that these soft theorems are mathematically linked to asymptotic symmetries of spacetime. This means that deep geometric structures dictate subtle particle behaviors. Such connections hint at a more unified understanding of gravity and quantum theory. Why does this matter for black holes? One proposal to resolve the information paradox suggests that black holes may possess subtle quantum features, sometimes informally described as soft hair. Traditionally, black holes were thought to be defined only by mass, charge, and angular momentum. The so-called Hare theorem. But if soft particles and asymptotic symmetries encode additional information, black holes might store information in ways previously unrecognized. If true, this would preserve quantum mechanical consistency while reshaping our understanding of gravitational systems. Pasterski's contributions lie in exploring and clarifying these relationships. Her research involves deriving mathematical results that connect scattering amplitudes, gravitational memory effects, and spacetime symmetries. These are not speculative philosophical ideas. They are rigorous calculations performed within the framework of quantum field theory. The intellectual challenge here is immense. The mathematics involves advanced tensor calculus, conformal symmetries, and complex variable techniques. Errors are easy. Precision is mandatory. Progress often appears incremental, but each clarification strengthens the conceptual bridge between gravity and quantum theory. Her work reflects a broader movement in theoretical physics that seeks unity not through grand speculative leaps alone, but through uncovering structural consistencies within known frameworks. Rather than abandoning established theories, this approach probes their hidden depths. Black holes serve as natural laboratories for this exploration. They are regions where gravitational curvature becomes extreme and quantum effects cannot be ignored. Understanding them requires merging insights from relativity and quantum mechanics. Another related concept tied to this research is gravitational memory. When gravitational waves pass through spacetime, they can leave permanent distortions in the relative positions of objects. This memory effect links observable phenomena to asymptotic symmetries. Such connections reveal that spacetime is not merely a passive stage, but an active participant in physical processes. By examining these relationships, Pasterski participates in reshaping how physicists think about the structure of reality. Instead of treating gravity and quantum mechanics as incompatible, researchers in this field look for shared mathematical foundations. This work also intersects with ideas from string theory and holography. The holographic principle suggests that information within a volume of space can be described by data on its boundary. Black hole physics strongly supports this idea. If information about what falls into a black hole is somehow encoded on its boundary, then the paradox may dissolve. While Pasterski's research is not confined to a single framework, it contributes to this broader conversation. By analyzing scattering processes and boundary symmetries, she helps clarify how information might be preserved. It is important to emphasize that theoretical physics at this level is not about dramatic public breakthroughs. It is about deepening mathematical understanding. Each paper builds upon prior results. Each derivation tightens the web of consistency. Working in this domain demands intellectual stamina. Problems may remain unresolved for decades. Progress can be subtle. Yet such persistence is how revolutions eventually occur. There is also philosophical significance in this line of research. For centuries, physicists sought to describe forces as interactions mediated by fields and particles within spacetime. But discoveries about asymptotic symmetries suggest that spacetime itself possesses richer structure than previously imagined. Perhaps gravity is not merely a force, but an emergent phenomenon arising from deeper quantum principles. Perhaps spacetime geometry is a macroscopic manifestation of microscopic information processes. These are the kinds of questions hovering at the edge of current research. Pasterski's work does not claim final answers. Instead, it sharpens the questions. Being called the next Einstein often oversimplifies the nature of modern theoretical physics. Einstein worked largely alone when developing relativity. Today's frontier research is collaborative and highly specialized. Yet the spirit of foundational inquiry remains similar. Examine assumptions, follow mathematical consistency, and seek unity in physical law. By focusing on black holes, quantum gravity, and the symmetry structures of spacetime, Pasterski aligns herself with that tradition. Another notable aspect of her work is its emphasis on mathematical elegance. In physics, elegance is not decoration, it often signals truth. When different equations converge toward a single structure, when symmetry explains behavior across scales, confidence in a theory grows. Her research contributes to identifying such elegant structures. Black holes once appeared as in points of understanding, regions where physics breaks down. Now they are viewed as gateways to deeper insight. Studying them forces physicists to confront the limitations of existing frameworks. The quest to reconcile quantum mechanics and general relativity may redefine our understanding of space, time, and causality. If spacetime is not fundamental but emergent, our conception of reality will shift profoundly. Sabrina Pasterski operates within this transformative zone. Her work represents careful excavation of the mathematical landscape underlying gravity. It does not rely on speculation alone, it relies on calculation. It does not abandon established physics, it probes its hidden consistency. In doing so, she contributes to one of humanity's greatest intellectual endeavors, understanding whether the universe operates under a single coherent framework. Black holes, once feared as cosmic abysses, now illuminate the path forward. Quantum fields, once confined to particle interactions, now intertwine with geometry itself. Spacetime symmetries, once considered peripheral, now appear central. Within this intricate web of ideas, Sabrina Pasterski's research stands as part of a larger effort to bring clarity where contradiction once reigned. If the 20th century belonged to the creation of relativity and quantum mechanics, the 21st century may belong to their unification. And in laboratories not of steel and glass, but of equations and thought, physicists like Pasterski continue the patient work of weaving gravity and quantum theory into a single, coherent understanding of reality. The phrase, "the next Einstein," carries enormous weight. It is not simply a compliment, it is a cultural symbol. Albert Einstein represents more than scientific achievement. He represents intellectual revolution. His name is synonymous with genius, with the reshaping of our understanding of space, time, gravity, and reality itself. So when a modern physicist is described with that comparison, it invites a deeper question. What does that label truly mean? In the case of Sabrina Pasterski, the comparison did not emerge from celebrity culture alone. It arose because of the level at which she works, the foundational layer of physics where the rules governing the universe are questioned and refined. Yet understanding why she is sometimes called the next Einstein requires separating media excitement from scientific reality. Einstein's greatness lay not merely in intelligence, but in his willingness to challenge assumptions. In 1905, his Annus Mirabilis papers redefined light, motion, and energy. A decade later, general relativity reimagined gravity not as a force, but as the curvature of spacetime. These breakthroughs required mathematical creativity and philosophical boldness. Modern physics faces a similar foundational challenge, reconciling general relativity with quantum mechanics. The tension between these theories remains unresolved. Black holes expose contradictions. The early universe raises unanswered questions. Space and time themselves may not be fundamental entities, but emergent phenomena arising from deeper quantum principles. Sabrina Pasterski's research operates directly within this arena. She studies gravitational physics, black hole information, scattering amplitudes, and spacetime symmetries, subjects that touch the very architecture of reality. Working at this conceptual depth naturally invites comparisons to Einstein because both focus on gravity and spacetime. However, the scientific environment today differs greatly from Einstein's era. In the early 20th century, theoretical physics was smaller and less specialized. Einstein could revolutionize physics largely through individual insight. Today's frontier research is more collaborative and mathematically complex. Discoveries often emerge from collective progress rather than solitary breakthroughs. So why does the comparison persist? One reason is intellectual temperament. Reports about Pasterski consistently highlight her independence, discipline, and focus on deep problems rather than superficial recognition. She reportedly avoids social media, keeps a low public profile, and concentrates on research. This mirrors the archetype of the quietly dedicated theorist, a trait often associated with Einstein's early years. Another reason is her trajectory. Building an airplane at 14 demonstrated not only technical ability but fearlessness toward complex challenges. Excelling at MIT and advancing to Harvard's theoretical physics program confirmed her mastery of advanced mathematics. Publishing work connected to black hole physics positioned her within one of the most profound scientific debates of our time. These milestones create a narrative that resonates with the public imagination, a young prodigy rising through elite institutions to confront the deepest mysteries of the universe. But the label "Next Einstein" can be both empowering and limiting. It is empowering because it signals recognition of extraordinary promise. It inspires young students, especially women in physics, by demonstrating that brilliance transcends traditional stereotypes. For decades, theoretical physics has been male-dominated. Seeing a young woman compared to Einstein challenges outdated assumptions and broadens representation in science. Representation matters because it reshapes expectations. When young students see someone like Pasterski working at the cutting edge of gravitational physics, it expands their sense of possibility. The comparison, in this sense, functions as cultural encouragement. Yet the label can also be limiting. It frames achievement through comparison rather than originality. No physicist can truly replicate Einstein's historical moment. Scientific revolutions arise from specific contexts. Today's challenges differ from those of 1905 or 1915. Expecting any individual to become Einstein misunderstands how progress unfolds. Pasterski herself has not claimed such a title. The comparison largely originates from media outlets eager to capture attention. Science communication often relies on familiar icons to help audiences grasp complex work. Saying "Next Einstein" is simpler than explaining asymptotic symmetries and scattering amplitudes. Still, beneath the headline lies a genuine point. She is working on questions as fundamental as those Einstein once pursued. Another dimension of the comparison lies in intellectual courage. Einstein questioned the nature of simultaneity and the constancy of light speed. He imagined riding alongside a beam of light. He trusted mathematical consistency even when it contradicted common sense. Similarly, researchers studying quantum gravity must question basic assumptions about space and time. Is space-time continuous or discrete? Is gravity fundamental or emergent? Does information truly vanish inside black holes? These are radical inquiries. Pasterski's engagement with such questions aligns her with the tradition of foundational thinkers. There is also the element of timing. Physics stands at a transitional period. The standard model of particle physics explains known particles and forces with remarkable accuracy, yet leaves gravity unincorporated. Cosmological observations reveal dark matter and dark energy, phenomena not fully understood. Theoretical frameworks such as string theory and holography offer possibilities but lack experimental confirmation. In such a landscape, young theorists working on gravity and quantum information naturally attract attention. The field is waiting for conceptual clarity. Any promising researcher contributing to that effort becomes a focal point. The comparison to Einstein, therefore, reflects both admiration and hope that someone may illuminate a path through current theoretical uncertainty. However, scientific revolutions rarely announce themselves in advance. Einstein was not widely recognized as a genius before his breakthroughs. Recognition followed achievement, not the reverse. In Pasterski's case, the narrative is unfolding in real time. Her career remains in progress. It is also important to emphasize that modern breakthroughs may look different from past ones. Einstein's equations were revolutionary because they replaced Newtonian gravity entirely. Today, progress may come through unification, reinterpretation, or discovery of deeper symmetry, rather than wholesale replacement of established theory. Pasterski's work on spacetime symmetries exemplifies this subtle progress. Rather than discarding general relativity or quantum mechanics, it seeks hidden connections between them. This approach reflects contemporary physics: refine, integrate, and reconcile. The comparison to Einstein also reveals society's fascination with singular genius. We often seek individuals to embody collective achievement. Yet theoretical physics is cumulative. It builds layer upon layer of mathematical structure. Pasterski stands within a network of researchers contributing to shared goals. Still, symbolic figures matter. They personify aspiration. When media outlets highlight her as a rising star, they draw attention to the importance of fundamental research that may not produce immediate technological applications, but shapes our understanding of existence. Calling her the next Einstein also underscores a generational transition. The giants of 20th century physics, Einstein, Bohr, Feynman, Hawking, are historical figures. The public wonders who will carry the torch forward. Young physicists working on quantum gravity naturally become candidates for that role. Yet perhaps the most accurate interpretation of the comparison is this: it signals that Pasterski embodies qualities associated with groundbreaking thinkers: independence, depth, mathematical fluency, and focus on first principles. Einstein once said that the important thing is not to stop questioning. By that standard, any physicist relentlessly probing the foundations of gravity and spacetime participates in his intellectual legacy. Sabrina Pasterski's journey from teenage aircraft builder to Harvard theoretical physicist captures the imagination because it combines technical mastery with conceptual ambition. The comparison to Einstein may be premature as a scientific judgment, but it reflects recognition of her potential and the seriousness of her work. Ultimately, the value of such a label will depend not on headlines, but on contributions. If her research clarifies aspects of quantum gravity, if it strengthens the bridge between general relativity and quantum mechanics, if it reshapes how physicists think about black holes and information, then history will define her legacy in its own terms. Einstein did not set out to become Einstein. He set out to understand light, motion, and gravity. Similarly, Pasterski's focus appears rooted not in titles, but in inquiry. Perhaps the true meaning behind calling her the next Einstein is not that she will replicate the past, but that she represents the continuation of a tradition, the tradition of questioning the deepest assumptions about reality. Whether or not the comparison endures, her work stands within the same grand pursuit, uncovering the mathematical structure of the universe and ensuring that our understanding of nature remains coherent, consistent, and unified. And in that pursuit, she does not need to be the next Einstein. She needs only to be the first Sabrina Pasterski, a physicist contributing her own insight to humanity's evolving understanding of space, time, and the fundamental laws that govern them. Scientific progress does not move forward through ideas alone. It moves forward through generations. Each era produces thinkers who inherit unanswered questions, refine old theories, challenge accepted assumptions, and expand the boundaries of knowledge. In this sense, Sabrina Pasterski represents more than an individual physicist working on black holes and quantum gravity. She represents a generational shift, a new wave of leadership in theoretical physics. For much of the 20th century, physics was defined by towering figures whose names became inseparable from their discoveries. Einstein reshaped gravity, Bohr and Heisenberg built quantum mechanics, Feynman reformulated quantum electrodynamics. Hawking transformed our understanding of black holes. These figures did not work in isolation, but they became symbols of their time. Today's physics landscape looks different. It is more collaborative, more mathematically intricate, and more globally connected. The problems are deeper, often more abstract, and sometimes less directly tied to immediate experiments. The next generation of physicists must navigate not only the scientific challenges, but also a rapidly evolving academic and technological environment. Sabrina Pasterski stands within this new generation. Her rise reflects a broader transformation in physics culture. Unlike earlier eras where access to elite institutions was limited to narrow demographics, modern theoretical physics is gradually becoming more diverse. While the field still faces challenges in representation, figures like Pasterski help redefine who can lead in foundational science. Her presence alone expands the image of what a theoretical physicist looks like. This shift matters because science thrives on varied perspectives. Different experiences can inspire different questions. Diversity in physics is not simply a social goal, it is an intellectual asset. When new voices enter the field, the range of inquiry broadens. At the same time, leadership in modern physics demands extraordinary technical mastery. The mathematics required to explore quantum gravity or black hole information is far more complex than what existed a century ago. Young researchers must absorb decades of accumulated theory before contributing something new. The bar for entry is high. Pasterski's trajectory through MIT and Harvard demonstrates that she has met this standard. But leadership is not defined solely by personal achievement. It also involves influence, shaping conversations, guiding research directions, and inspiring others to pursue difficult questions. One of the defining characteristics of her public image is intellectual seriousness. She does not cultivate celebrity culture. She does not rely on dramatic self-promotion. In an age when visibility often overshadows substance, this restraint sends a powerful message. Ideas matter more than image. This approach contrasts sharply with modern digital culture, where personal branding can dominate professional identity. By keeping her focus on research rather than publicity, she models a form of scientific leadership grounded in depth. Another aspect of generational leadership lies in interdisciplinary awareness. Today's theoretical physicists often engage with ideas from mathematics, computer science, and information theory. Concepts like holography, quantum entanglement, and space-time emergence connect gravity research to quantum information science. The boundaries between disciplines are increasingly porous. Pasterski's work on scattering amplitudes and spacetime symmetries situates her within this interconnected landscape. Such research requires fluency not only in classical relativity, but also in modern quantum field theory techniques. The ability to bridge conceptual domains is a hallmark of contemporary physics leadership. Moreover, the next generation must balance theoretical ambition with empirical humility. Many frontier theories, including aspects of quantum gravity, remain experimentally unverified. Physicists must navigate this uncertainty carefully, pushing conceptual boundaries without drifting into unfalsifiable speculation. The discipline required to maintain that balance is significant. It involves grounding abstract mathematics in physical principles and seeking consistency across frameworks. Pasterski's focus on symmetry structures reflects this careful methodology. Rather than discarding established theory, she probes its hidden connections. Leadership also includes mentorship and visibility within academic communities. While her career is still developing, young physicists who see someone close to their generation working on foundational problems may feel encouraged to follow similar paths. Inspiration can ripple outward in ways that are difficult to measure but powerful in effect. The symbolic dimension of her role should not be underestimated. For young women interested in physics, seeing representation at the highest theoretical levels can counteract stereotypes that persist in STEM fields. It reinforces the idea that intellectual ambition knows no gender. At the same time, reducing her significance solely to representation would diminish her scientific seriousness. Her leadership arises first from intellectual contribution. Representation amplifies impact, but substance defines it. Another feature of modern physics leadership is global connectivity. Conferences, collaborations, and publications link researchers across continents. Theoretical progress often emerges from collective refinement rather than singular revelation. Participating effectively in this network requires communication skill, clarity of thought, and openness to critique. Physics seminars at top institutions are famously rigorous. Ideas are challenged immediately. Calculations are scrutinized. Assumptions are questioned. Thriving in such an environment requires confidence without arrogance, the ability to defend reasoning while remaining receptive to correction. Pasterski's academic path suggests comfort within this culture. Contributing to high-level research conversations signals intellectual maturity. There is also the question of long-term influence. Leadership in theoretical physics unfolds over decades. The next generation inherits unresolved puzzles: the true nature of spacetime, the unification of forces, the explanation of dark matter and dark energy. Solving even one of these would redefine scientific understanding. While it is too early to predict ultimate breakthroughs, positioning oneself at the heart of these questions is itself significant. By dedicating her research to gravity and quantum structure, Pasterski aligns her career with the deepest challenges available. Generational leadership also involves continuity. Physics evolves, but it builds upon its past. Einstein did not erase Newton, he extended and refined him. Quantum field theory did not discard classical mechanics, it generalized it. Modern researchers must honor this lineage while pushing forward. Pasterski's work embodies that continuity. She operates within established frameworks, extracting new implications from their mathematical structure. This careful advancement ensures that progress remains coherent rather than fragmented. In the broader public imagination, science sometimes appears stagnant because breakthroughs are less visibly dramatic than in earlier eras. Yet, beneath the surface, conceptual refinement continues steadily. Leaders of the new generation carry that quiet momentum. Sabrina Pasterski represents this momentum, disciplined, mathematically rigorous, and focused on first principles. Whether or not she ultimately reshapes physics in revolutionary ways, her presence signals that foundational inquiry remains vibrant. The future of theoretical physics will not be defined by nostalgia for past geniuses, but by the sustained efforts of researchers willing to wrestle with its hardest problems. In stepping into that role, Pasterski exemplifies a generation prepared to continue humanity's search for unity in the laws of nature. Leadership in science is not about replacing legends. It is about extending the frontier. And in dedicating her work to gravity, spacetime, and quantum structure, she stands among those prepared to guide physics into its next chapter. The future of fundamental physics stands at a crossroads. For over a century, scientists have relied on two towering frameworks to explain reality: general relativity and quantum mechanics. Each theory has passed every experimental test within its domain, yet together they remain incomplete. Their mathematical languages resist full unification. Their assumptions about space, time, and information do not seamlessly align. This unfinished reconciliation defines the central mission of 21st century theoretical physics. Within this mission lies the broader significance of Sabrina Pasterski's work and the legacy she may help shape. To understand the road ahead, we must recognize the scale of the challenge. General relativity describes gravity as geometry, spacetime bending in response to mass and energy. Quantum mechanics describes the universe in terms of probabilities and discrete interactions. One treats spacetime as smooth and continuous. The other reveals that at microscopic scales, nature behaves in granular, sometimes counterintuitive ways. When these two frameworks meet under extreme conditions, at the center of black holes, or during the earliest moments after the Big Bang, inconsistencies appear. Mathematical infinities emerge, predictive power collapses. Physicists know that a deeper framework must exist, one that contains both theories as approximations. This search is not merely technical, it is philosophical. It asks whether spacetime itself is fundamental or emergent. It asks whether information is the true currency of reality. It asks whether gravity is a basic force or a macroscopic effect arising from quantum interactions. Researchers like Pasterski are positioned within this search. Her work on black hole physics, scattering amplitudes, and spacetime symmetries contributes to understanding how gravity behaves at the quantum level. While no single paper can resolve the unification problem, each careful calculation strengthens the conceptual scaffolding required for progress. The legacy of such work may unfold gradually rather than dramatically. Scientific revolutions often appear sudden in hindsight, but they are built upon decades of incremental refinement. Einstein's general relativity did not emerge from nothing. It grew from Maxwell's electromagnetism, Newton's mechanics, and the mathematical groundwork of Riemannian geometry. Similarly, any future theory of quantum gravity will emerge from layers of careful theoretical exploration. Pasterski's engagement with asymptotic symmetries and soft theorems reflects one promising direction. These studies suggest that spacetime contains deeper symmetry structures than previously recognized. Symmetry has historically guided major breakthroughs. When hidden symmetries are uncovered, conservation laws and unifying principles often follow. If future developments reveal that black hole information is preserved through subtle boundary effects or holographic encoding, then today's investigations into scattering amplitudes and gravitational memory will be seen as foundational steps. Another dimension of the future lies in technological advancement. New observational tools are transforming physics. Gravitational wave detectors have already confirmed Einstein's predictions about spacetime ripples. Black hole imaging has moved from theory to reality. Quantum computing is beginning to test ideas about information processing at fundamental levels. These experimental breakthroughs may intersect with theoretical insights in unexpected ways. Theoretical physicists must remain adaptable, ready to refine models when new data emerges. The ability to bridge mathematics and physical interpretation will be crucial. Pasterski's background, combining disciplined engineering in her youth with high-level theoretical research, symbolizes this bridge. Her early experience building an airplane grounded her in applied physics. Her later work explores abstract gravitational theory. That combination reflects what the future of physics may increasingly require: thinkers comfortable with both conceptual depth and physical reality. Legacy in science is not determined solely by individual fame. It is measured by influence on ideas. If her contributions clarify aspects of quantum gravity, inspire new lines of research, or mentor future scientists who achieve breakthroughs, her impact will extend beyond personal recognition. There is also the cultural dimension of legacy. The image of who can lead in theoretical physics is evolving. When young students see someone from a new generation working on black holes and the structure of spacetime, it reshapes their expectations. Inspiration can have exponential effects. One visible figure can motivate thousands of future researchers. The future of fundamental physics will likely involve collaborative networks rather than solitary geniuses. Complex problems demand diverse expertise. Progress may arise from integrating perspectives across mathematics, cosmology, particle physics, and quantum information theory. Within this collaborative era, clarity of thought becomes even more important. Researchers must communicate complex ideas precisely. They must identify which assumptions are essential and which can be modified. They must navigate uncertainty without losing rigor. Pasterski's measured public presence and emphasis on research over publicity align with this need for intellectual focus. The legacy of fundamental physics will depend less on dramatic headlines and more on sustained dedication. It is also possible that the ultimate unification of gravity and quantum mechanics will redefine our understanding of reality as profoundly as relativity once did. Concepts such as spacetime emergence, holography, or quantum entanglement may transform not only physics but philosophy. If spacetime emerges from deeper informational structures, then our intuitive notions of distance and causality could be approximations rather than fundamentals. Such a shift would echo the transformation Einstein initiated when he replaced absolute space and time with relative spacetime geometry. Whether Pasterski herself authors such a breakthrough remains unknown. Science does not operate on predetermined narratives. What can be said is that she is engaged precisely where such breakthroughs would occur. The pursuit of quantum gravity may take decades more. It may require entirely new mathematics. It may demand experimental insights not yet possible, but progress is cumulative. Each careful derivation, each clarified symmetry, each resolved inconsistency narrows the gap. Legacy, then, is not about inheriting Einstein's title. It is about contributing to the continuity of inquiry. Einstein once reshaped our understanding of gravity. Today's generation seeks to understand gravity's quantum nature. The thread connecting these efforts is the refusal to accept contradiction as final. In this sense, the future of fundamental physics belongs to those who remain patient with complexity and persistent in questioning assumptions. Sabrina Pasterski's career embodies that persistence. From early demonstrations of discipline and courage to advanced research at the frontier of gravitational theory, her trajectory reflects commitment to foundational understanding. The ultimate structure of the universe remains an open question. Is reality fundamentally geometric, informational, quantum at every scale? The answers await discovery. If the coming decades yield a deeper synthesis of the laws of nature, historians may trace its origins to the careful work being done now, in equations written quietly, in symmetries analyzed precisely, in paradoxes examined patiently. And within that unfolding story, the legacy of those who dared to explore gravity's quantum depths will stand as part of humanity's enduring quest to comprehend the universe in its most fundamental form